Laser Interstitial Thermal Therapy, or LiTT, merges optical engineering with neurosurgery. The procedure involves inserting a fiber-optic laser probe into the brain to ablate abnormal tissue using heat. What makes it unique is real-time MRI monitoring, allowing surgeons to visualize and control thermal spread with millimeter accuracy. LiTT has gained traction since the 2010s due to advances in MRI thermometry, fiber design in laser systems. The engineering challenge lies in balancing power, precision, safety within the constraints of neurosurgical navigation. Throughout this presentation, we'll look at the hardware architecture, laser sources, fiber optics, applicators, cooling systems, and MRI integration, and how each contributes to procedural accuracy and patient outcomes. LiTT's roots trace back to early neurolaser experiments in the 1960s, which revealed both the potential and danger of intracranial laser use. Continuous wave lasers like CO2 improved precision but lacked real-time temperature feedback. The 1980s saw ND-YAG lasers used to induce controlled coagulation, laying the groundwork for modern interstitial therapy. MRI and CT guidance in the 1990s enabled trajectory planning, but limited feedback during ablation. The real breakthrough came with MRI thermometry in the 2010s, allowing real-time temperature visualization. This evolution reflects a convergence of optics, electronics, and imaging technology that defines LiTT today. A complete LiTT system is a coordinated network of hardware and software. The laser console generates controlled light pulses, typically near infrared at 1064 nanometers. The fiber optic cable transmits this energy into tissue through a cooling sheath that maintains probe integrity. The MRI system provides thermal imaging feedback to the workstation, which displays real-time thermal maps for the surgeon. The integration of all these components ensures precision and safety. Engineers must synchronize laser output, imaging refresh rates, and system communication protocols to maintain thermal control and avoid collateral damage. The laser source, often ND-YAG, produces near-infrared light that penetrates brain tissue efficiently. Energy is delivered through flexible optical fibers designed to withstand high thermal loads. Sapphire fibers are preferred for their durability and low absorption losses. At the distal end, a diffusing tip scatters light evenly, creating a symmetrical thermal field. Engineers implement interlock systems and temperature-limited feedback to prevent overexposure. Cooling channels circulate saline around the fiber to dissipate excess heat. The precision of this delivery system determines both treatment effectiveness and tissue prevention. MRI guidance transforms LiTT from a manual ablation to a data-driven procedure. Engineers design software that integrates MRI datasets with navigation coordinates, allowing precise targeting of deep brain structures. A stereotactic frame or robotic arm precisions the laser probe with sub-millimetre accuracy. During ablation, MRI thermometry tracks heat diffusion by measuring T1 weighted signal changes. This real-time monitoring lets clinicians adjust laser power or duration dynamically. For engineers, the synchronization between the MRI system, workstation, and laser console is critical. Timing mismatches can lead to inaccurate thermal estimates or safety risks. Thermal management ensures that the system ablates target tissue without damaging adjacent structures. Engineers design cooling sheaths that circulate sterile saline around the laser fiber, maintaining consistent temperature gradients. The coolant removes excess heat from both the probe and surrounding tissue near the entry point. This prevents charring and optical fiber degradation. Real-time temperature readings from a thermocouples inside the probe feed into the workstation, enabling precise control of ablation zones. This combination of passive and active cooling mechanisms is what allows LiTT to operate continuously and safely within a narrow therapeutic temperature window. MRI thermometry is the feedback engine of LiTT. Engineers leverage the proton resonance frequency shift, a phenomenon where tissue temperatures alter MRI signal properties to create live temperature maps. The workstation overlays these maps on anatomical images, allowing surgeons to see ablation margins forming in real time. Algorithms estimate thermal dose and cumulative energy delivery to predict tissue necrosis. This closed feedback allows fine-tuning of laser output mid-procedure. Accuracy in image registration and temperature calibration is vital, as even a 1-degree deviation can alter the predicted damage zone. The workstation functions as the operational core of LiTT. It consolidates all data streams, MRI images, temperature readings, and laser parameters into a unified interface. Engineers develop intuitive GUIs to visualize ablation zones and control laser emission profiles. Built-in algorithms calculate estimated tissue depth zones, while safety systems issue alerts when thresholds are exceeded. The software architecture must ensure low latency data exchange between MRI and laser console. Any lag or desynchronization could compromise safety. Integration testing, redundancy protocols, and cybersecurity features are key components of the system's reliability. From an engineering viewpoint, LiTT is a carefully choreographed process. Pre-operative MRI defines the target and trajectory. The surgeon or robot guides the probe into position under image navigation. Calibration ensures alignment between physical and digital coordinates. The laser system then delivers energy in controlled pulses, while MRI thermometry verifies safe heat distribution. After the ablation phase, imaging confirms lesion containment and absence of collateral damage. Each stage depends on hardware communication, fidelity, imaging accuracy, and precise actuation of mechanical components. Safety in LiTT relies on both design and maintenance discipline. Systems must conform to IEC 60601 laser safety and electromagnetic compatibility standards. Engineers implement interlock that shut down the laser if cooling flow stops or if MRI synchronization fails. Routine calibration verifies energy delivery and optical alignment. Fiber connectors and diffusers are inspected for microfractures or residue buildup. Cooling pumps and saline circuits undergo periodic leak and pressure tests. Every maintenance cycle ensures that precision and safety parameters are preserved, allowing consistent therapeutic outcomes. So what are the future directions in LiTT engineering? LiTT continues to evolve through innovation in optics, robotics, and data science. Engineers are miniaturizing laser consoles and probes for smaller access routes, expanding applicability to previously inaccessible regions. Robotic integration enhances accuracy and reduces operator fatigue. Automated feedback control, where the system modulates laser power based on real-time thermometry, promises greater precision. Cloud-based analytics will enable remote monitoring, performance benchmarking, and predictive maintenance. The trajectory of LiTT engineering reflects the broader movement toward minimally invasive intelligent surgical systems.